Good morning, everyone. My name is Herb Jasak. Welcome to the two-day course on OpenFOAM at the HPC Center of University of Ghent. The task that we have is an almost impossible one because I don't know my audience. So in order to prepare for this course, I have prepared 11 sets of presentation slides, and I've got another 20 if we need to complicate things. And I have prepared a set of tutorials which are all pretty easy ones, but I have hidden difficult things as well. Just to help me out a little bit, can we do a show of hands of who is doing OpenFOAM for the first time? Okay, and who is an experienced OpenFOAM person like Peter there? 1, 2, 3, 4, 5. As I said, this is an impossible job. Okay, so after the coffee, may I please ask you to move yourself either to the left side of the room or the right side of the room, just to help me out with the task that I will give you. Okay. Now, the point of this course is that we are going to do special wishes as well. And I got a list doing from everything from GGIs to dynamic mesh to solid mechanics to fluid structure interaction, which is again impossible. Okay, so the topics that I have chosen to do here is a set of tutorials, discretization best practice, which is probably the most important presentation that we have to do. And out of physics topics, I have used only the multi-phase free surface and film. Okay, how many people do we have who need to do, for example, combustion? You're on your own? Okay. How about dynamic mesh? Okay. You're both advanced, I hope so. Right? Okay. You know nothing and you want to do dynamic mesh on day one? Fine, I can do it, no problem. Okay. And turbulence? Okay, so we have quite a lot of people on turbulence. So what we're going to do is we are going to do practical examples of doing a turbulence course. Now, do you have access to an OpenFOAM installation that you can use? Yeah, everybody? There is an installation on the system as well. If you want to follow me, especially if you're a beginner, please try and log into the system and use Foam Extend 3.2. That's mainly because I have checked all the examples with it and I know where the bugs are. But if you're advanced and you prefer a different version of OpenFOAM, by all means do that, and we will do little changes along the line that we have to make this work for you. Okay. So there are two files that have been prepared for you. Blah blah blah. Training cases and training slides. Okay, so the training slides will contain all of these, and if we choose to use some additional slides as well, we will make them available. Okay, out of the goodness of your heart, please do not put it on your internet site. On intranet it's fine, but I do quite a lot of these courses and the slides change. So just for courtesy, please keep them within your organization. Okay, since we have beginners in the audience, I have to do a couple of hours of very beginner-like stuff. One is the user view presentation. That's number one, to give you an idea of what is going on. And then we will do a number 2 presentation, which is a simple tutorial. Okay? My beginners, have you done any tutorials so far? No? Hands up for no? Hands up for yes? Okay. Do you mind doing them again? Okay, fine. What about the advanced people? Shall I give you something more complicated to do while we're playing with this? Or are you happy to listen with us for another hour? Okay, so what we will do is I will ask you to listen for the first tutorial, and then I will give you something that is a little bit more advanced than just running the case, and I will give you an hour to do that. Okay, this is a standard job that I give usually at the beginning of the second day of training. So if you're really good, you'll finish it in 10 minutes and then you can relax and have coffee. If you're a little bit slower, you'll finish it in about an hour and then you can show some impressive presentations. Okay, how hard would you like to work? I can survive about 4 hours standing here, but you cannot. Okay, so now it's 9:15. Shall we have a break at 10:30? 10:30 till 11, 10:45 for coffee? And then lunch at? Are you 12 noon lunching in Belgium, or?
Typically, yes.
Okay, lunch at 12? Okay, fine. Afternoon tea? Don't say 5 o'clock, please. Okay, so we'll have an afternoon break at around 3. And what time shall we finish? The room is booked till 6, but you're not going to survive, and I may not either. Okay? 5:30? Tomorrow morning, does anyone need to leave early?
Yes.
What time?
4:30.
Okay, so we'll make sure that for the last sort of hour is an open discussion and you get to ask your questions first. Okay, 9 o'clock, is it okay to start for tomorrow? I have to tell you a story. The scariest presentation that I did was in Finland. Okay, there were 65 people in the audience and they were just looking at me. Okay, so please at least smile. Okay, if you have something to say, do interrupt me. Okay, meshing. Do we need to do meshing? We'll do a little bit of meshing for the beginner's course. And last question, how many from academia, how many from industry? Academia, hands up. Everybody's academia. Good, okay. Do we have to worry about running Fluent and CFX and Star CCM and that sort of thing? Is that what you do now? No? Good, okay. So we will learn how to, tell me.
I use Fluent a lot, so I don't use OpenFOAM, so probably if you could tell how this interface works, it would be better.
Okay, well the syntax and the interface we will do. Some of the mesh conversion we will do as well, and then we will play around. Okay, so let us start with the first part of the introduction.
For the people that want the slides locally, I just sent you a mail with the slides and so on. Practical.
Okay, if this gets boring or too detailed, etc., wave your hands, move on. If you don't understand something, say, hey, stop. Please ask me questions, okay? If I get bored, I will start talking faster and faster and faster and faster and faster, and then it's going to be Tuesday afternoon and there is no point, right? Okay, please interact. So what we will do for the beginning is start with a little review of the user view. The idea is that I can provide you some basic information about the software from the user's point of view. At this point, I used to start talking a lot about C++ and object orientation and that sort of thing. And if you're using Fluent, you don't really care. You want a CFD solver that works, you want to know how to use it, and you want to know how to efficiently generate the results. So the points of the story is, what is this thing, how do I run it, and what capabilities does it have? What we will do is go through an executive overview, and then what it means to run OpenFOAM and how it is different from commercial CFD packages. And in the end, we'll just give a few points of interest. When I finish with this presentation, we will go through a tutorial, which I will do step by step. Okay? For the advanced people, by all means, grab a cup of coffee, listen to your radio, play with anything, play crosswords. This will be boring, but we have to do it in order for the beginners to know what is going on. Okay? After that, of course, it gets more interesting. Right. So OpenFOAM is a free-to-use open source software with numerical simulation, CFD, and multi-physics capabilities. Okay? Number of users, I estimate to about 60 or 70,000 today, which is absolutely amazing because there was 10 of us in the room when it all started. Free to use means you don't pay the software. Okay? It does not pay for your time. It will not buy your own computers, so it still costs a lot of money. Okay? Especially on the computers. It runs on HPC machines. The biggest runs that we have done so far is about 10,000 core, and in fact we got thrown out of the Argonne National Lab cluster, which is one of the really big computers in the USA, because on input-output the damn thing opened 70,000 files and knocked over the cluster. Okay, so it works, but it's not perfect. My customers regularly use about 2,000 cores without any problem, and with scaling which is better than commercial CFD software. The software is under active development, and the capabilities are pretty close to what you're going to get in commercial CFD. How do I know? I spent 4 years working for CD Adapco. I spent 8 years consulting for Fluent, so I know exactly what's in these codes, and I'm quite happy to compete. Okay. There is a substantial user base in industry, academia, research labs, national labs, etc. And there are two good points about the software. Number one, it is free. And number two, it works. Okay? This is not a magical software that will solve everything for you by itself. It is actually quite difficult to learn compared to clicking buttons on Fluent, for example, but it does work. Okay? Other good things about it is that there is a possibility of extending it to solve the physics that you have to solve. For the last 6-7 years, I have been doing lots of naval hydrodynamics, which means CFD, moving bodies, mooring systems, wave generation, blah, 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 that you do not expect to see in your CFD life. And also, it is perfect for sharing. If you need to share your work with other research groups, or you need to provide results of university research to industrial clients, you're quite free to send them the source code and share it with them. Now, open source is not a way to steal your intellectual property. Okay? So you're free to do with the software what you like, and there is no obligation to share the results. Okay? So when we are developing the propellers, for military applications, that source does not have to be shared, and there are ways of protecting the intellectual property that you wish to protect. However, if you do not share the source, then the source is your problem. As versions move forward, the software gets upgraded, better, faster. It is your job to maintain your software, and this is why projects like OpenFOAM and Foam Extend exist for someone else to look after the software and make sure that it works. Okay? Of course, that means that in order to contribute, you need to be able to write commercial-grade CFD software, and this is what you're here to learn. Okay, what are the main components? Well, the first thing is that the software is significantly different than other commercial CFD software on the market, and it feels like a set of Lego bricks. Okay, you know Lego? Found it in my hotel this morning, so there must be Lego in Belgium. Okay. And the idea is that there are things that we need to do which are the same or almost the same across a range of applications, and they can be shared. Okay? So rather than having one big executable, like for example in Fluent, with an if-then-else loop, we have a set of capabilities libraries. What do I mean if-then-else loop? When you start running Fluent, it will start reading the case file and say, is my flow laminar or turbulent? It is turbulent. Which model do I have? K omega SST. So you're going to have if K epsilon, if RNG K epsilon, if K omega SST, if. Is my flow single phase or multi-phase? Am I solving energy equation? Yes or no? Is radiation on or off? Yes or no? Etc., etc., etc. Okay? Of course, the number of possibilities is really huge, and not all possibilities match. Okay? In OpenFOAM, rather than having one big executable, we are going to have lots of small executables that are written specifically for the job. So the first step will be, I'm trying to solve steady state, incompressible, turbulent, single phase flow around a NACA airfoil. Therefore, I will use simple foam, which is one of our executables. Okay? All of the executables are about this big. They are meant to be read by you, meaning normal human beings rather than super programmers. Okay? And they use the components from my Lego set to make sure that there is as little code at this top level as possible. What are the components? Well, the first one is discretization. We implement the polyhedral finite volume method, which is second order accurate in space and time. We also have Lagrangian particle tracking, so you can shoot particles through your mesh, and to the particles you can attach some physics. Okay? Examples of physics being attached is nothing. Okay? Just track some particles through the domain. Or diesel spray, okay? Where you have breakup and coalescence, collision, wall collision, evaporation, drag terms, volumetric chemistry of the particles, exchange of mass and momentum and energy with the continuous phase, etc., 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 which will model the diesel spray. Okay? We also have something called the finite area method, and the idea here is that we can solve a 2D approximation of the finite volume method on a curved surface. Okay? So this will be for applications like liquid film, for example. Okay? We also have massive parallelism in domain decomposition mode. What does that mean? It means that we will take one big mesh, we will chop it up into bits, assign one bit on each core, and make them speak to each other at programmatic level to make sure that they behave as if they are one big simulation. Okay? More on that later. We also have automatic mesh motion, topological mesh changes, interface to thermodynamics library, thermophysical models library, transport models, turbulence models, radiation models, etc., etc., etc. Okay? Once we have all of those, they will be implemented in a library form, and we will model the physics that we need to have using something called equation mimicking. What's the trick? Well, the trick is that the finite volume library is much more powerful than just doing the fluid flow. Okay? The obvious example, of course, is stress analysis. But to give you an idea of what we can do with foam, I will tell you a little story about the two most impressive projects I've done so far. The first one was biscuit baking. Okay? So the idea is that you take some dough, you put it into the oven, you heat it up, the dough rises, and you can take a look at the quality of your biscuit. Okay? Is this continuum mechanics? Yes, because you're solving transfer of mass, momentum, and energy. Let me describe. Okay? So what we will do is we will start with a mixture of liquid, water, and a solid. We will heat it up from the surface. The water will start evaporating. As we get rid of the water, there will be a chemical reaction, which will convert the dough into bread. Okay? As a part of that, some of the energy will be taken out, and the material properties of your material will change into something that looks like a porous medium. Okay? With the porous medium, you will have the flow of water vapor out and the flow of air in through the porous medium. The properties of the porous medium will depend on the composition, liquid, contents, and temperature. In the end, you will make a crust on the outside, which will seal the outside part of your product. As you evaporate water, your internal pressure will make the bread rise. When you use up all the water, it settles a little bit, and the process is finished. So what you have here is first conservation of mass. Solid material, liquid water, water vapor, air. Then you have conservation of momentum, which is flow through a porous medium. You have conservation of energy, which says the energy that comes onto the surface by convection or radiation will be conducted and transported by the move of water, vapor, and air. You also have the other momentum equation, which says my bread is actually a piece of solid, and under the internal pressure it will rise. And when you cook it all up together, you get a model of a biscuit. Okay? Now, doing that with a commercial CFD code is almost impossible because it assumes that you're going to solve the momentum equation, the energy equation, you will have this kind of fluid and that kind of fluid. But in fact, my discretization and all of the other tools are still the same. So the idea is that we will do implementations of the physics model that you wish to have using something called equation mimic. So the idea is this. We speak of continuum mechanics. So this is my conservation of mass, momentum, and energy. And the continuum mechanics already has a language, which is partial differential equations. So what we have here is a transport equation for the turbulence kinetic energy, dk by dt, div uk, Laplacian, source, and sink terms. And we will represent it as this piece of software here. So I have 8 lines of software that will solve this equation on a given mesh in parallel, blah, blah, blah. Okay? Now, this is all quite impressive, but not what you need right now. Okay? So apart from being able to write your own equation, the code will give you the capabilities to solve the problem that you wish to have with minimum amount of messing. Okay? So, what kind of problems can we solve? The first one is some basic things, like solving a Laplace equation, potential flow equation, passive scalar, vector, and tensor transport. Then incompressible and compressible fluid flow, mainly using segregated algorithms. In foam extent 3.1, we came out with block-coupled algorithms, and we can do a tutorial with it if you want. Heat transfer, buoyancy-driven flow, multi-phase, etc., all the way up to stress analysis, fluid structure interaction, etc. Now, those pieces already exist for you, and they are ready to run. So if you want to do CFD or flow around the Formula 1 car, you will pick up one of these solvers, which is incompressible, turbulent, steady solver, and just do the simulation as if it is in a commercial software. However, assuming that so many of you is out of academia, you probably have your own equations which are not quite on the list that you wish to solve. And with foam, you can pick out the components and put together your own solver. Okay? The first step that you need to know is how to run the stuff that you already have. Okay, so here's a little overview of how the system operates. So we have the components, foundation libraries. Those are basic things like what is a vector, what is a tensor, how I do a dot product of two vectors, time database, which says my simulation will start at time 0, it will finish in time n, it will progress in time steps. I will have the mesh, which is the discretized form of my computational domain. And then I'm going to have the whole of the discretization, in this case, second order finite volume. Okay? Then we have the physical modeling libraries to help you with things like, for my biscuits, what are the properties of water vapor as a function of pressure and temperature. Okay? Of course, I can do the same with liquid water plus the full whole interface for combustion. Okay? And then we have all of the other models as well, like viscosity models, turbulence models, chemical reaction interface through ChemKin, interface to material properties through Janaf tables, etc., etc., etc. At this level, it really helps you that OpenFOAM is not such a new thing. Okay, so the earliest pieces of software were written in 1992, which is almost 25 years ago. So all of these interfaces have been validated and people have been using it for a long time. The second part of the story is something that I called utilities. Okay? So these are all the things that you need to have in order to run a simulation. We will start by mesh generation, or stealing meshes out of ANSYS, Pointwise, CFX, StarCD, etc. Then mesh import and manipulation. Okay, so if you want to turn your mesh, mirror your mesh, stretch your domain, blah, 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 all of these tools already exist. We have some mesh generation capability as well. We have parallel processing tools to allow you to deal with massively parallel machine, like domain decomposition, data reconstruction, etc. And we have my customized executables. Now, probably the easiest part of the story is interfacing with external software. This is an open source code, so if you have your own library which solves the 6 degree of freedom mesh motion equation, or gives you properties of materials that are not within, say, JANA for ChemKin tables, you can integrate with them. Most of these interfaces we will find in cases of, say, fluid structure interaction, where you want to calculate things like a flying shape of a sail on a sailing boat, and then you have a structural analysis software for the structural part, and you want to use OpenFOAM for the CFD part, and make them speak to each other to get the actual fluid structure interaction simulation. Each of the executables is only a few hundred lines of code, and I will take you through one of those probably tomorrow morning, scalar transport form, and I will do it line by line. I need you to understand what is what and what comes where as a preparation for the coding. And you will suddenly see that this is not as scary as it is. One more rule. The software has been written for you to guess things. Okay? So the magnitude of a vector will be called mag. Okay? The sign of a floating point number will be called sign. Okay? So do bravely try and guess, and if it isn't, then start looking. And the software should not hurt you. Okay. The other thing that I need to know is how to organize my case. Unlike in Fluent or StarCCM, where there is a case file, we have a case directory. Why is that? Well, if you're running a large eddy simulation around a car on 120 million cells, then your data file can be 2 terabytes. This is suicide. Okay? Really, we would like to have a database which will manage the file data that you can manipulate and blah, blah, blah. But this was started by 2 PhD students in desperation rather than by a team of computer scientists. So instead of having a file, we used Unix. Okay? My case will be the case directory, and inside of the case directory, there will be 3 main components. The first one is the system directory, the second one is the constant directory, and then there is a bunch of time directories. The idea is this. In the system directory, there will be items that control your simulation. For example, in the control dictionary, we will have start time, end time, time step, when to input and output, etc. In the FV schemes directory, I will set up the discretization parameters for various equations that I'm solving. And in the FV solution directory, there will be the solver-related parameters. Now, please note, the library doesn't know what you're doing. Okay? Nowhere in the library does it say you have to solve fluid flow for Newtonian fluids, which means that each of the executables will have slightly different things in FV schemes and FV solution. So how do I deal with that? Well, in 2 ways. The first one is, with every executable, there should be several tutorials. Okay? So when you're using a new executable that you don't know about, please do start from the tutorial. run the tutorial, find out what it does, then throw away the mesh, put in your mesh, and start adapting the tutorial. Okay? The second thing that you need to learn is what are the keywords and values that belong into these dictionaries. Okay? For that, you have to let the code fail and tell you what is missing. Okay? Do read the error messages. Okay? Later on today, I will teach you something called the banana trick, but I will save that one for later. Okay? Finally, in the constant directory are the bits that remain constant during your simulation. For example, material properties, choice of turbulence model, choice of chemical reaction model, computational mesh. Okay? You will see that even in the computational mesh, which is really one object, I'm going to have input-output organized by components. So my points, faces, cells, and boundary will be separate files within the system. Okay? All of these files are meant to be looked at by a human. Okay, so open an editor, find out what's in them, play around. This is where the banana trick lives. Finally, I'm going to have a set of time directories, typically starting with a directory called 0, which is my initial field. What will be in that directory? Well, I don't know. If you're solving steady, incompressible, turbulent flow, I can guess that you're going to have the pressure field, the velocity field, some sort of turbulent representation, say k, omega, and mu t, and maybe something else that depends on the solver. Okay? How do you know? Look at the tutorial. Okay. When we have organized things like that, and we run the code, it will create further time directories that will contain the results and the ability to restart from any of those. Okay? So, with the controls in the control dictionary, you will control how many time directories you have. Please note, there are no hidden variables, there are no hidden states, and this is a purely Unix file system. Okay? So if you have too many time directories, delete them. Okay? One of the possibilities that the software will give you is use of compressed input-output. Why is that? Because these files are full of numbers, and if you want to store, reduce the amount of file storage on disk, you just use the gzip format, and FOAM will happily read the gzip files. Okay, so apart from running the simulations that I told you about, there are some issues that need to be done by a lot of codes, like extracting the data. Okay, the typical example is I'm solving a transient flow simulation and I want to know the pressure value at XYZ position. Okay? The idea of dumping out all the time steps and then picking up the values later on is completely out of the question. We need to be able to pick up that data while the code is running. Okay? Any other examples of data like that? Well, when we run a large eddy simulation, I don't just need to have the instantaneous velocity field, but also the average. Or, if I'm running a really big simulation of a ship on waves and I'm just interested on the free surface, I may not wish to output all of the details of the simulation on disk. I just grab isosurface of the free surface and then visualize it some other way. There is, of course, lots and lots of those, and they are done in a different way. But most importantly, they are done consistent with discretization. Okay, so if you want to know mass flow rate through one of the outlet patches, there is a way to ask the code to calculate that while the code is running rather than later. Okay, another example, forces and moments on a moving ship during the simulation. Okay. There is also the graphical post-processing hookup, and our favorite tool nowadays is called ParaView. What's so great about it? Well, number one, it's free, and number 2, it works. Okay? So this is the one that you get for free. There are also interfaces for field view, Insight, and various other things that are sort of comfortable, okay? But it really depends how much you like them, because these tools cost money. Okay. Now, please note, when you run OpenFOAM, I cannot promise you one thing, and that's to type OpenFOAM. There is a flashy user interface coming in front of you, and you do the clicking. Okay? Indeed, there is a few of these user interfaces, but they limit you in the things that you can do. Usually my second and third year students start using a user interface. They're really happy with it for about 3 weeks, and after that they throw it away and they start editing files by hand. So I will just jump you those few weeks ahead. Now, what's so interesting about OpenFOAM? Number 1, it is an open architecture. You have access to the complete source code. You can see all the bits. If you don't like them, change them. Okay. Number 2, there is support. And number 3, it can be used as a common platform from shared projects. Okay. So when we have several universities or universities and commercial companies collaborating with each other, they are free to exchange the code, and it goes really quickly and really well. Okay. Low-cost CFD. It doesn't cost you anything apart from computing power and electricity in order to run this code. Now, please note, I still want a €100,000 computer, and nobody is going to buy it for me just because I run OpenFOAM. But there are happy people here in the HPC Center in Ghent, which will provide you academic access or even commercial access to the software. Okay? Number 3, the numerics and discretization does not know what you are doing. What does that mean? At no place in the code can I say, oh, I'm solving fluid flow, therefore convection terms are going to be more important than diffusion terms, and I will make my code run faster by doing blah, blah, blah. Because the person next to me is running structural analysis where this is not the case. Okay? So the transfer of best techniques from various areas happens all the time. And things like, for example, with the block-coupled solver, we started doing nuclear reactor simulation, then we did pressure-velocity coupling, now we're doing solid mechanics simulation using the same code base, because it's the right thing to do. And finally, this is an efficient environment for complex physics problems. Okay? So if your problem gets worse and worse and worse and worse, you can start with the tools that you have, run them for a little bit, and then say, yes, but I really need to take into account the energy equation, okay? And add a set of modules to solve the energy equation. Yes, but I really need to take into account conjugate heat transfer. Yes, start building up the conjugate heat transfer. And by doing that, you can build your own tool which uses the library components that are already there, that have been validated separately, to do the right thing. That's it for the first set of slides. Any questions? You want to run this damn thing now? Okay, so can you log into the system and open up the first tutorial? And we will do it side by side, very slowly with the explanation. Is it possible to log into the system?
Just in de baas, voorlopig denk ik ook nog geen goed. Is it just a small test case?
Yeah, it's 11,000 cells.
Okay, so just a second. Just use the login as well. Anybody needs help with logging in, or slash ops? CD of ls slash ops ls en dan zullen we Ja. Voor de hands-on best wel. Ja. Ik heb er nooit in
ik ken het van ja, en met parafiet zit.
Waar staat het?
Ja, dat is wel, ja.
Ja, gewoon dat zijn dan zo'n PowerPoint of daar niet.
Kies en heel goed. Wel? Ik wil het complicated en heb je het gedaan?
Als je de versie van
Als je niet hebt gedaan, dan hier.
Dit is gewoon op je account. Op je hart is het dat je dat kan lezen.
You have to do there's a slash do
Ja, maar nog een duur laten. Heb je die meer moeten zeggen?
Wow, I'm looking into the. Jullie zijn niet de VC.
We're trying to get him online.
Wat?
En dan moet je.
Ik weet niet. Ik ben source. Ik ken het niet zo. We zeggen, waarom zit het niet af aan? Dit is goed. Ja, misschien.
Nee.
Oké, goed. Ja, dus nu moeten we dat volgen.
Ready? Anyone still stuck? Stick your hand in the air so that people can help you.
you have a
I'll
come back to you.
I'm actually. Dan heb je zien en je moet terug laden. Allee, proberen laden, maar je kan ze niet laden. Ik heb die module afgegeven.
Dat is volgende week.
Heb je iemand die list dat je OpenFOAM gedaan?
Ja, die is het.
Heb je iemand die list om zorgen dat je kunt elke module laten, kun je
Ja, dat is sowieso.
Als je een complex krijgt, dan moet je drie volgen.
Ja, de uiteindelijke bedoeling is als je.
Ja, maar ik ben nu aan het.
Nee, maar dat zijn allemaal zijn implementaties. Dus wel, was wel een folder die cases. Ja, en daar staan ze. En wat hij wie de nacht
Ja, als je nu
die twee taskfiles geschreven?
Yeah, so you can't use them.
Ah ja, zit in de run. Ah, zit de source. De run cases staan in de cases zelf staan in run. Ja. En daar die knokken. Dat gaat u niet zetten.
Ja, we gaan dat binnenkort posten. De volgende week. Zo kun je dat op het moment dat je de opstart doet. Er moet een paar gebeuren
Die 16 A, hè.
Voilà, nu staat er wel op.
En je hebt geen voor extent
We hebben wel
een
4000
extent met
het zijn maar heel van 3000 aan. Dus dat wel. Maar de CPU-visualisatie is iets van.
er is een paraplu versie.
Ja, dit.
Dus er is wel een before extent 3.3 met dit. En dat is samen laten
Ja, ook bij andere geen technologie.
Can you do it into the key generator?
Ready? Shall we start?
Deze al, ik heb nu alleen dit OpenFOAM.
Ja, de rijden zijn al wel.
Ja,
Ik weet niet of dat kan.
die van binnen.
Ja, dat was nog staan.
Ik kan het doen, maar dat is. Als we met Unix zijn, dan is het nog wat anders.
Okay, so I will be using the set of slides called NACA Wing Tutorial. And on the training cases, you have run/NACA 0012. So the first time around, I will go through it by looking at the slides. And then we will go through it again by looking at the actual case directly.
OpenFOAM Bluetooth en de motherboard op. Ah, daar hebben we.
Ja. Switch again.
Okay, so the job here is to do a flow around a 2D NACA airfoil, and we will use the steady, incompressible, turbulent Rams solver called SimpleFOAM. The steps that we will do are the basic review of case organization, mesh conversion, set the boundary types, set viscosity, review the zero directory, and then come back to the rest of the list. Okay. So as I said,
Yes. Okay, just maybe do a reply to the mail.
we want to solve the flow
Yeah.
around an airfoil, and we will use the inlet velocity of 242 meters per second, P infinity, T infinity, etc. And in order to do that, we have to go through the organization of the files.
Ik zie dat net.
Okay?
Maar het is
Have you seen this picture before? Are we okay now? Okay, so as I said, we are going to have the system directory where the controls are, the constant directory with various properties and the mesh, and a bunch of time directories. Each of the files has got a little description of the header. Are you guys done? You done? Okay, so each of the files will have a little description of the header telling the system that this is a FOAM file. Okay? The format looks like this, and later on I will describe this to you as a dictionary. Okay? A dictionary is the main input-output system of OpenFOAM. The idea is that everything in a dictionary has got a keyword and the value, for example 2.0, ending with a semicolon. Okay? So the way you search the dictionary is you look for the keyword and get everything from here to the semicolon to interpret in your way. Okay? The first dictionary that I have here describe this to me as an OpenFOAM file, and the dictionary starts and ends with open and close curly bracket. Okay? The format is close to something that computer scientists will call XML. You know XML? Unfortunately, we were there before XML, so we had to invent our own format. Okay? The properties, the object that has got that lives in this file is called transport properties, and the properties that it will have depend on the kind of solver that I have. Okay? So for a more complex property, I have an entry for diffusivity here. Okay? As we said, the keyword is the part called dt, and the value is everything from here to the semicolon. Okay? This property will be a dimension scalar, and as a C++ object, a dimension scalar has got 3 bits. The first one is a name, dt. The second one is the set of dimensions: mass, length, time, temperature, molar concentration, electric current, luminous intensity, or mass, length, time, temperature, molar concentration, electric current, luminous intensity in the SI way, and then the value. Okay? So when I read dt and perform field operations, more on that later, I will be able to check for the dimension set. Okay? Solution fields, initial, boundary conditions, solver controls, input-output parameters, etc., are all given in a dictionary format. My main dictionary is something called the control dictionary. At the top of the control dictionary, there will be a little entry saying foam file that allows me to look at the dictionary. Okay? And then I'm going to have a bunch of keyword value pairs. Okay? So for C++ programmers, the comment style in this dictionary is the same as the comment style for the C++ source code. Meaning, everything that starts with /* and ends with // is a comment, and everything that starts with // ignores the rest of the line. Okay? Take a look at it here. Start from, start time is 0, stop at, end time is 2,500, delta t is 1. What does that mean? It means that the solver will count time steps 1, 2, 3, 4, 5 and stop when it reaches 2,500. Happy? Now there is a slight misnomer here, because if I'm running a steady state simulation, then delta t doesn't make sense. But as I already told you, the solver doesn't know what physics you're doing, so we have to choose one way of dealing with it. Okay? The second part that I have here is write control. What does that mean? Do you remember the time directories, 50, 100, 200, etc., where the solver dumps the data for me to look at them? Well, how often do I want to have that? I want it to output every 50 timestamps. Okay? Another bunch of parameters here, like write format, ASCII, write precision 6, write compression on or off, time format, runtime modifiable, etc. Okay, now at this point, the first time you see OpenFOAM, you're really in trouble. Because here, I tell you start from start time, but what are the other options? Okay, so here I have written some of the options here. So start from latest time. What would that mean? Well, take a look at the bunch of time directories have been written out, pick the one with the biggest value, and start from there. So this would be good for restarts, for example. Okay. Other options here, write control. Write every 50 time steps. Of course, I have other options. For example, if I'm running a transient simulation, I want to see the results every 1.5 seconds. In that case, I will do write control, run time, meaning the simulation time, and write interval 1.5. Okay, and the code will write every 1.5, 3, 4.5, 6, etc. seconds. Okay? Now, this can get more complicated as well. For example, if I am running the time step control, where the solver determines its own time step, and I still want to have the dumps exactly at 1.5, 3, 4.5, and 6 seconds, then I will use something called adjustable runtime. More on that later. Okay. One more parameter here, write format, ASCII or binary. Now, what does that mean? It means that the data part of my files will be written in binary format, and later on today, I will show you what that looks like. The point of the boundary format is twofold. Number one, you get full precision, and number two, the code writes faster. Okay? However, it will not take care of the big endian, little endian pipe kind of story. So if you have to move the data from one computing platform to another, please write ASCII, restart, and then switch back to binary if you're really happy. Okay? Now, the last entry is quite important. It says runtime modifiable, yes. What does that mean? Well, the idea is that the software will read its control files when it starts, but my CFD simulations don't last 1/10 of a second, they can last for 2 weeks. Okay? So if something starts going wrong, or I don't like some of the settings, I need to have the option of talking to the solver to change the settings. Okay? So when the runtime modifiable flag is set to true, that means that every time step, the solver will check with the filing system whether its control files have changed. Okay? If they did, it will reread them and apply the new parameters. Okay? Now please note, it will not actually read the files every time step. It will just query the filing system whether the change time has changed since the last time it saw the file, which doesn't cost you much. Okay? So in this way, you will be able to control your running while the solver is going ahead. I will show you some examples of that in a minute. Okay? The second file that I have is called FV schemes. Okay? So those will be finite volume discretization schemes. Okay? Do you remember my K equation? It had the DDT of K and convection and diffusion and various sources and sink terms. And basically, each of the terms in each of the equations that you're solving needs to have an entry for the kind of discretization that I'm going to have. Now here's the problem. My file doesn't know what it's solving. Okay? So this needs to be a very flexible format. And here is an example. The DDT scheme is my rate of change scheme, and my default scheme will be called steady state. Grad scheme will have a default which is cell limited least square 1.0, and my div scheme will have various schemes for various entries here. Okay? So if you look at this a little bit more carefully, you can tell me that I have a convection term for the equation called U. What would that be? Velocity, right? I have a convection term for the equation called K. That will be turbulence kinetic energy, etc. And I have a bunch of choices here which are not trivial. Okay? You really want to pull down menu with all the available choices, but unfortunately we don't have that. So what's the trick? Well, number one, you don't know what entries the solver needs to have. And number two, you don't know what the possibilities are. So if you're really desperate, delete everything out of the contents of my schemes and put something like default none. Okay? What the solver will do is it will go through the equations that it's solving, and for each term in each equation, it will say, fatal error, I don't know how to discretize div phi u. Okay. At that point, you can add an entry for div phi u, but you still don't know the right-hand side. Here comes the banana trick. Write banana, semicolon. Okay? What the software will do, it will say, I don't know a convection discretization scheme called banana. No surprise. Your available choices are blah, 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 blah. Okay? And then from the available choices, you can choose the one that's available. Okay? There is another way. You know what equations you're solving because you know what problem you're solving. And you can guess quite a lot of these. Okay? And even to this day, especially with that one and that sort of thing, I still let it fail and I find out what is available. For those who need to do this simulation over and over again, number one, start from the tutorial. Number two, set up something that we can call a template case. These are my default settings with a dictionary. Make sure that they work once, and every time you start with something new, start from that case. Okay. The second part of this dictionary looks like this. Laplacian schemes, interpolation schemes, SN-grad schemes, flux required. And some of them can have a default entry and then specific override for some of the factors. Okay? We will see that at least 20 more times during the course, so I'll let it go for a little bit. The next part of the story that I have is the FV solution file. Okay? Again, it has a series of dictionaries. How do you recognize them? Solvers, open curly bracket, close curly bracket, is a dictionary of dictionaries. Okay? The first dictionary has got a keyword P, open curly bracket, close curly bracket. The second dictionary has keyword U, open curly bracket, close curly bracket. Can you guess what this is? Well, these are the linear equation solver settings for a variable called U, which is probably velocity, right? Peter disagrees because in his case it is displacement increment, but who cares? That's because Peter is using a different solver. Okay? What are the parameters? Well, the first parameter is which solver do I want to use, and that one is called BCG with ILU preconditioning, and it's got an absolute tolerance and a relative tolerance, or maybe many more parameters. Okay, two wrinkles. Number one, what solvers are available for you? Anyone? Come on, you know, I told you a second ago. Stick in a banana, and you will find out what the choices are available. Okay? Number two, the pressure matrix is symmetric, but the velocity matrix is asymmetric. How do you know which solver to use? Well, you don't. But the choices of linear equation solvers for symmetric matrices and asymmetric matrices will be different. So if you want to know what are the symmetric solvers, stick a banana in here, and you will find out what is available. Okay? I will talk about tolerances and relative tolerances a bit later. The second part of that file has got two more dictionaries. The first one is called PISO, okay, which is for the algorithm that we are using to solve things. It can be PISO, simple, potential flow, block solver, what you like. And again, by knowing which solver you use, you will be able to use the appropriate algorithm. And the second one is relaxation factors. Okay, so by now you know the game. In order to solve a simple based segregated pressure velocity system, I have to provide relaxation factors for all the variables that I'm solving. So what does this line say? Well, it says the keyword is P, the value is 0.3, which means that the relaxation factor for the variable P is 0.3. Okay? What happens if I stick a banana in here? The solver will say, fatal error, I expected to read a floating point number, and I read a word. Okay? So at least it will tell you what it expects to read, which is very useful if you have more complex discretization schemes. Okay? For those advanced users, there is one more thing that I wish to mention, and that is related to the way the schemes are written out. Okay? So take a look at it here. Div, phi, u. For the div, I will use the Gauss's theorem. Phi is already defined on the faces. I don't have to worry about it. Okay? And for u, I will use a linear upward scheme, which needs a gradient. And the gradient will be Gauss with linear interpolation. So as you read it from left to right, you will be able to build out the scheme. What about the Laplacian? For the Laplacian, I have div, gamma, grad, u. Div, Gauss, gamma, linear interpolation. Grad u will use a scheme called limited 0.5, which is exactly the same as this surface normal grad scheme, limited 0.5. Okay? As you get better at understanding discretization and you run more cases, you will get better at guessing as well. So let us now take a look at the definition of my mesh files. So we said that in constant polymesh directory, there will be my mesh. Okay, so this is the discretization of space. What does it look like? Well, number one, I have to have a series of x, y, z locations for the points, which will be an object of the type point field. How many points in the list? The same as the number of points in the mesh. Then I'm going to have faces, owner, and neighbor, which is the way of defining my faces and cells. Okay? A face is defined as an ordered list of points where the point index is equal to its location in the list. Okay? And a cell should be defined as a list of faces where the face index is its point in the face list. But I don't like that. Why is that? Well, very simple. Because some cells have got 5 faces, some have 8, some have 26. Right? So instead of storing the owner, the cell as a list of faces, for each of the faces I will store the owner and the neighbor cell, meaning the cell to the left and to the right of my face. Okay, why is that so good? Because a face is either between 2 cells or between 1, in which case it is a boundary face. Okay? So my internal faces have owners and neighbors, and the boundary faces all only have neighbors. We can also have additional things in the list, like point zones, face zones, cell zones, mesh modifiers, sets, etc. But we will speak more about those when we start talking about dynamic mesh. Okay? Finally, one of the important files in the mesh is called a boundary file. So what we said is that some of the faces in my mesh will be on the outside, and on those I need to specify a boundary condition. Okay? They are grouped in a file called boundary. Okay? Here I'm going to have a list, C, round bracket, of dictionaries, and each of the dictionaries will have several things. Number 1, patch name. Number 2, patch type. Number of faces in the patch, and the start face, because the mesh is ordered so that the internal faces come before the boundary faces. What is that for? Well, it is to help me with the definition of boundary conditions. Okay? So, for example, all of the faces on the wing will have the same velocity, which is 0 meters per second. All of the faces at the outlet will have the same pressure, which is 0 Pascal. All of the faces at the inlet will have the same turbulence kinetic energy, which is 0.03. You got the idea? Okay, so to help myself defining the values face by face, I will group the faces the way I see fit. What happens if you have two outlets? Outlet 1, outlet 2, different conditions of those outlets, everybody's happy, right? So nobody tells you how to group the faces apart from you, okay? So when we started doing Formula 1 simulations, we used to get meshes with something like 300 patches, okay? Why? Because they want to calculate the force separately on the front wing, back wing, pod, driver's helmet, blah, blah, blah. This is up to the user, okay? But the patches can be organized any way that they like, and they can be ordered in any way that they like, okay? Now please note, here it will say things like wall or patch or empty, okay? But it will never say things like inlet. Why not? Because the library doesn't know what you're solving. So if I'm doing a magnetohydrodynamic simulation or an electrostatic simulation, or simulating biscuits, what does inlet mean to me? Nothing, okay? So the idea is that here I will label patches only if they mean something special in the geometry, okay? So a good example would be a symmetry plane. Why? Because if something is a symmetry plane patch, it is a symmetry plane for pressure, velocity, temperature, what you like, okay? And the only sort of exception is this one which says wall, and that one indicates that for the turbulence model, when I measure the distance to the wall, this is the patch that I will speak to. Happy? More to follow. In the next step, I am going to have fields. Okay? The field will exist in the time directory. Okay? They will be named depending on what they are. P, T, U, K, omega. You probably can guess all 5 of those. So P for the pressure, T for the temperature, U for the velocity, K turbulence kinetic energy, omega eddy turnover time. Okay? Now notice, some of those fields are scalar fields. Some of them are vector fields. I can also have fields like grad U, which is a second rank tensor, etc., etc., etc. Okay? When I write out the fields, I have the following entries. Dimensions: mass, length, time, temperature, molar concentration, electric current, luminous intensity. So what's this thing here? Meters per second, probably velocity. Okay? I have the internal field, which says uniform 40, 0, 0. What does that mean? It means that for all the cells of my internal field, the velocity will have XYZ component of 40, 0, 0. Okay? The boundary field is a dictionary of dictionaries, and have a look here. I have the name like body 4. On that I have type, which is fixed value, and the value, which is 0, 0. Got it? Then I have type inlet 12. open curly bracket, close curly bracket, type fixed value, value 4000. Where will these names appear? Constant polymesh boundary, right? Now, when I specify the fields for the solver, this is all fine, and this is nice and easy to read for me. But when the solver writes out the results, then the value of the field will not be uniform, right? So what I will have is it will say something like non-uniform list of vector, open round bracket, and then the number of vectors, which is equal to the number of cells in the mesh. Okay? For the boundary conditions which are not uniform, I may have the same, but whenever possible, I will try and avoid writing things like, for example, on a zero gradient boundary, because I can easily figure it out from the other data. Okay, so my initial and boundary conditions will be defined in zero directory, and the consistency of those boundary conditions depends on the solver. Okay, so here I have to make you work harder than you work with, for example, Fluent, and you need to know that the inlet means a fixed value of velocity, fixed value of turbulence kinetic energy, dissipation, temperature, blah, 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 but, for example, zero gradient on the pressure. Yes, but if your solver is compressible and the flow is supersonic, then you will fix the pressure at the inlet. Okay? Also, you have about 5 different ways of specifying the turbulence kinetic energy. It can be a given value, it can be a percentage, you can give dissipation in terms of the length scale, blah, 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 which means that these conditions that we had on the previous slide can get more and more complex depending on how luxurious you want your life to be. Okay? For example, if I have an inlet patch which is not aligned with x, y, or z, I may wish to specify the inlet velocity as something like mass flow rate. Okay, which means the mass flow rate is 40 liters per second. Now you go and figure out the area of the patch and the direction and specify the fixed value which corresponds to my mass flow rate. Okay, so those are the kinds of things that foam can do. Finally, we have a lot of utilities that also have controls under system. Okay, so the file that I have here is called the decompose par dict. Anyone can guess what that is? If you run in parallel, you have to decompose the mesh into bits. And this one will tells me that the number of subdomains is 4, and the method that I want to use is called metis, and it will decompose into 4 bits with equal weights. Okay? I think that's enough of the preparation. And for a change, let's try and run something real now. Unfortunately, 10:30. Let's have coffee first. Any questions so far? Are you still alive? Good. I promise it will get more interesting. See you in half an hour.